Hi, and welcome back to another Math 104 lecture. So today what we're going to be looking at is we are going to be finishing up logarithms. Now, we have a couple last topics that we have to go over. Now, there's only two topics that we have to do, but they are not intuitive. So I want to make sure that I go through them pretty slowly and pretty carefully, so that way we all understand what's going on with, at least a couple of examples for each. Okay. Except for the last topic, which is somewhat lengthy, so there's only going to be one example. So the first topic that we're going to look at today, and also just to recap, in the last lecture, what we looked at was our three rules. We have three rules that we looked at for logarithms. I can't talk. Product rule, quotient rule, and power rule. Right? Product rule is it allows us to add any two logarithms together as long as they have the same base, right? If we have log of a and it has some value attached to it plus log of a, also, notice same base. As long as they have the same base, you can take your two values, and we know that the product rule says, okay, well, if we have two logarithms added together, it's the log of the values of both of those logarithms being multiplied together. So m times n, right? And of course, the base stays the same. And then we have the quotient rule, which says effectively something similar, but it just allows us to subtract our logarithms. So if we have log of some base a minus log of the same base with some other value m, then it allows us to condense it into a logarithm, into one single logarithm with the same base. But this time it is n over m, right? So addition, again, implies multiplication here inside the one logarithm. Subtraction of two logs implies a division. So n over m. And you know which one's going to be your numerator based off of which one is, based off of which one is positive and which one is negative, right? We see the subtraction is tied to that log base a on m. So that's how we know that the m is going to be in the denominator. Okay, so those were our two rules for adding and subtracting logarithms, also known as respectively product and quotient rule. And our last rule is the power rule, which says if we have some log with some base and it has a value with an exponent, again, keep in mind this entire piece is inside the logarithm, then what we can do is we can take our exponent, move it out front, and it can become our coefficient. So we can bring the r outside and make this r times log of base a on m. And of course, everything that I just said, the opposite is true as well as far as the direction that you're going, right? So I basically wrote all three of these rules out, stating that if you were adding two logs, then you could turn it into one log. If you're subtracting two logs, you can make it one log, and if you have an exponent, you can bring that exponent out, right? But the converse is also true because this is an equal sign, right? We can go back and forth. So the converse says, okay, well, if we have one logarithm with two things being multiplied inside, we can always break it up into two logs separated by addition. If we have one log where there's division going on inside, we can separate it by subtraction into two logs. And last but not least, if we have a coefficient in front of a logarithm, we can always move that coefficient to be the exponent on the value inside the logarithm. So it doesn't matter what direction you're going, these rules will hold true. These are just, standard logarithm rules. But now notice, as far as how we're handling logarithms, like logarithm operations, we have a rule that helps us with two logs being added. We have a rule that helps us with two logs being subtracted, but we don't have a rule so far for some log multiplied by another log. We also similarly do not have a rule so far for one log being divided by another log, and that's what we're going to explore today. So these aren't necessarily multiplication or division rules. It's just something that happens to fall out of a process. Now, the process that we're going to be looking at in essentially the topic that we're looking at is called change of base. So change of base effectively says if you have a logarithm and it has, some base, you can always change it into a fraction that has two logarithms of a different base. So to write it out, change of base. What's going on here is, once again, if we have log of some base a on some value, what we can do is we can take this one single logarithm and we can make it a division of two logarithms where they both have the same base. And in fact, you get to choose what that base is, or the directions in a specific question will tell you what the base should be. And so once again, log base b, where b is just some base that you are deciding for it to be, or the directions are specifying it for you on your value, the original value, and log base b on your original base. So I know that this sounds, again, this is not really intuitive. Let's break down what's going on here. If we're just following where the letters are moving to, again, you're starting with one logarithm, right? You're starting with a log. It has some base. It doesn't matter what the base is, and it has some value. It also does not matter what that value is. The only thing that matters is that obviously the value and the base should be defined for all logarithms. And once again, going back to when we first introduced logarithms, we still have the same general rules, right? A has to be positive. A cannot be 1, and also x must be positive, right? So your value must be positive as well. As long as it meets these three rules, a and x it doesn't matter what those numbers are. We can always use change of base. So how do we use change of base? And why do we use it? Well, one of the reasons why we use it, other than for the fact that sometimes it actually might clean up an equation, is on your calculators, for I'd say 99% of the graphing calculators out there, and also 99% of the online resources out there, there are log calculators where the only logarithm buttons on your calculator are log, which is supposed to be, again, we talked about this is a common log, right? If the base isn't present, then it's base 10, right? So your calculator would have a log button, and it would also have a natural log button. But short of that, say, for example, you wanted to evaluate the following. If you wanted to evaluate, let's just hypothetically say, log of base 3 on the value 5, well, it'd be very difficult to plug this into a calculator. Being able to plug in the base 3 onto a calculator, again, for most calculators is quite a challenge. So what we can do is we can change the base to be something that we can actually plug into a calculator, so that way we can actually get a real value from this. It's something that is easily able to plug in. So again, one more time, just to go over the process of how you change your base. The idea is simple. First, you determine what b should be. B, again, being your new base. So if you want b to be 10, that's fine. Just understand that you're going to have two logarithms, one over the other, where they're both in base 10. Okay? But for the sake of argument, it could be any number. Okay? Once you determine what your new base should be, the rest is pretty boilerplate. Your base goes to the bottom. Your value goes to the top. Your base becomes the new value of the logarithm in the denominator, and your value from the original logarithm becomes the new value of the logarithm in the numerator. Again, the way to think about it, the way to remember it, base, bottom, right? So this is already it's already lower underneath. It's a subscript, right? So this is in the bottom, and it stays in the bottom. It just becomes the value now, okay? And once again, your old value is still a value, but just in the numerator. Okay, let's get some practice in with using change of base here. Once again, if you wanted to change it, to be in terms of base 10, so if you wanted this to be, a common log, you could just say log of x over log of a. And identically, you could also do the same thing for natural log, where you would have natural log of x over natural log of a. And the neat thing is that these are actually all equivalent. It doesn't actually matter what your base is, as long as you're making sure that your old value is still your new value up in the numerator and your old base is your new value in the denominator. It doesn't matter what your base in the what your base of the logarithms are, as long as they match. Again, the key thing here is that the logarithms match here. Okay, and if you were, for example, just hypothetically, if you plugged in log of, let's say, I don't know, log of 8 over log of 5, this actually gives you the exact answer as if you plugged into your calculator the natural log of 8 over the natural log of 5. Okay, so it doesn't matter what the base is. Again, keep in mind for this one the base is 10, for this one the base is e. That's the whole idea of a natural log. But what's more important is just that it matches on the top and the bottom, and that the values are the same going from, one log to the next. Okay, so again, let's go ahead and get some practice in with change of base. First, what I want to do is I want to find, let's find log of base 3 on the value 15. I want it to be in base 10. So I'll write this out in base 10. And then once it's in base 10, what I want to do is I want to evaluate it in a calculator. Again, notice how in this form, log base 3 on the value 15, this is really difficult to plug into a calculator. This is not something that you could easily do on your TI-84. I'm assuming that's what we're still on, TI-84, maybe. Maybe it's gone up from now. I don't know. I'm old. In any event, so this would be very difficult to plug in there. But once we change the base, it becomes far more easy to plug in. So what I want to do is, again, first we start with our first logarithm, right? Log base 3 on the value 15. Now the directions say we want it to be in base 10. So we already established what the base is going to be of our two new logarithms, right? So we know we're going to have a division. This is what change of base does. It's the division of two logs. So we have log over log. And I'm omitting the 10 because, again, log base 10 is just the common log. So I can just write the log. I don't need to write the actual base. If you did write log base 10, that's okay, but you don't need to. And now we just need to figure out what these values are. Well, once again, think base goes to bottom, right? So we know that if 3 is my base of the original logarithm, then the value 3 is what's going to be in the bottom logarithm, the logarithm in the denominator. So this is going to be log of 3. And the value from the original logarithm becomes the value in the numerator logarithm. So this is log of 15. And now log of 15 and log of 3 are two totally acceptable things that you can plug into your calculators. And when you do that, this is approximately, it's not exact because it is irrational, but it is approximately 2.465, right? So the idea here is that you wouldn't be able to evaluate this in the form that it's in, but if you can change the base to be something more accessible, like again, 10 or E, then this absolutely becomes way more able to be evaluated. And of course, when you plug it into your calculator, you do get the answer, about 2.465. If you round it at any point, that's totally fine. What I'm mainly getting at is how to apply change of base. Okay, so again, just to quickly recap, the idea here is to change the base. First, you decide what you want your new base to be. In this case, the directions told us base 10, so that's how we knew to use the common log. So again, common log, base 10. The next thing is all we have to do is just figure out the values and where they're going. The base of the original is the bottom value, and the value of the original is the top value. And that's all there is to it. That is change of base. Okay, so let's run through a couple more examples here. So let's say I wanted to find log of base 5 with the value 14 in base E. Okay, so once again, we're starting with our original logarithm. Our original log is log base 5 on the value 14. We know it's going to be a division of two logarithms when we go ahead and break this down into change of base. And now it says in base e, right? So this is log of base e, log of base e. But we have a special name for this, right? If we have a logarithm in base e, well, this is just the natural log. So we don't even have to write log base e. We can just write ln, natural log. So log base e just implies natural log. So we have the natural log over a natural log. Now what we need to do is, okay, we have the logarithm, we have the base figured out, we just need to figure out the values. So figuring out the values one more time here, the base of the original becomes the value of the bottom. So we're having the base of the original was 5, so we have the natural log of 5 in the denominator. For the top, well, this is easy, process of elimination, even if you forget, as long as you remember where the bottom value is going to be. The top is going to be the original value, right? So we have log base 5 on 14. That 14 is what's going to go into the top logarithm. So we have the natural log of 14. And we're done. I'm not going to ask you guys to, evaluate this with a calculator. If you want to, totally acceptable. But the point is that now you understand we have some garbage logarithm. We can turn it into more easily accessible logarithms. And again, we don't have to pick e or 10 just because they're on the calculator. You can turn this into any single logarithm with any single base that you want. Again, assuming it's not 0, non-negative, and not 1. Right? That's just all the rules of logarithms. As long as it's a positive number that's not 1, you can make it whatever base you want. You just need to make sure that the bases match on the top and bottom of your fraction. Okay. So with that being said, what I want you guys to do is we're going to have our first classwork assignment. So the first classwork assignment is the following, okay? So I'm going to give you givens here. Let's say given log of x is equal to 3 and log of y is equal to 6. I want you to evaluate the following. And the following is log base x of y squared. Okay, so give this a shot, see what you can come up with. Again, evaluate means that you're trying to get a number back, right? Your final answer should be some sort of number. So see what you can do, and of course, unpause the video when you are ready. Okay, so going at this, well, the first thing that we see here is that we have the given log of x and log of y. But what we want to do is the first thing we want to establish is the bases of these logarithms. Notice how the base for both of these are common logs, right? So the base is 10. So that means that when I inevitably try to change this into a form where I can get log of x and log of y, that means I know that my logarithm has to have the base of 10, right? But furthermore, we can't just jump directly to it. I mean, we can, and if you did do that, that's totally acceptable. But notice that we have this exponent here, right? So whether we deal with it now or deal with it later, totally acceptable either way. I personally am just going to deal with it now. Okay, so dealing with it now means, well, remember our power rule, right? If we have an exponent tied to a value inside of our logarithm, power rule says we can take the exponent and just move it out front, and that becomes our coefficient of the whole log, right? So let's go ahead and do that. So we're going to make the 2 that was the exponent into a coefficient now. So we have 2 times log base x on the value y. Again, notice now we don't have this exponent. It moved over to be the coefficient, right? And that's just what power rule allows us to do. Okay, so we have 2 times this log right here, right? So what we want to do is we want to try to use change of base here to get it in base 10. Because if we can get it in base 10, then obviously we'll be more in line with what the given information was. So change of base formula says, okay, well, I'm going to have the division of 2 logarithms, log over log. And I'm just going to leave it as log because base 10 implies it's a common log, so I don't need to write the base. Remember, I still have the 2 that's out front, so it's 2 times this entire piece. And last but not least, we just have to figure out the values on the top and the bottom. Remember, the base of the original goes to the value of the bottom logarithm. So this is log of x. And the value of the original logarithm goes to the value of the numerator. So log of y. And now, well, now we can just directly substitute in, right? We know what log of x is. We know what log of y is. So substituting in, this should give us 2 times 6 over 3, right? Log of y is equal to 6. Log of x is equal to 3. So with that being said, we have 6 over 3, which gives us 2. We still have the 2 out front, so we should get 4 back. And that should be your final answer after evaluating. Okay? So again, what I did was I handled this exponent first. And just to show that it's totally acceptable to handle it after the fact, you can do the change of base first. And just to reiterate that, if we had, again, starting from the beginning, log base x on y squared, if you immediately jumped to the change of base, that's totally acceptable. Again, log over log. Again, the base becomes the bottom value. So that means that I'm going to have log of x down here. And when you're figuring out this value, don't forget to take the entire exponent with you. The exponent comes with that value, right? The exponent is tied to that value. So it's log of y squared. Okay, and now you might know what log of x is from the given information, but we don't have the information for log of y squared. But this is now where you would just apply that power rule, right? So applying the power rule now just gives you 2 times log of y over log of x. And when you simplify this, well, this just gives you 2 times log of y. So 2 times 6 over 3. 2 times 6 is 12 over 3, and we get 4 regardless. Okay, so either way, however you do it, whatever order you did it in, absolutely acceptable. The main idea here is just understanding how to take one logarithm, change the base of it, so that way we have more accessible bases, bases that suit our needs given the information or given if we wanted to evaluate using a calculator. Okay, so that's that for change of base. However, again, what I was saying earlier was that we had, no formula for division and for multiplication, right? So again, just to quickly recap one more time, as long as your base is the same, log a of m minus log a of n, well, we can handle this, right? Subtraction of logarithms we can absolutely handle. And addition of logarithms we can also handle. So now what we just found out is we can now handle division of logarithms. Because what was change of base formula? Change of base formula, so log base a on the value x. What happened? Again, we had log of some base over log of that matching base of a, right? So what was going on? Well, this is the division of logarithms. If we're going backwards, if we wanted to, we could absolutely go backwards this way. Going backwards just, says, okay, we have 2 logarithms being divided. What's going on here? Well, what's going on is that you have to realize if we wanted to move backwards, the bottom value is your base of your new logarithm. And your top value is the value of your new logarithm. And of course, these bases here, the b's, are just going to drop out. These no longer play a part because your new base is a, just like we just said, right? So division of logarithms is also acceptable as long as the bases match. So if we have, again, just writing change of base formula in the opposite direction, if we have log of base b on some value x and same base, log of base b on some value a, what's going on is that we can condense this to be log of base a on the value x. So all I did was I just rewrote the change of base formula. Instead of left to right, I wrote it right to left, but of course that means the same exact thing. So now notice, great, we can handle logarithm subtraction, we can handle logarithm addition, and we can handle logarithm division. But what about multiplication? Okay, so for multiplication, again, it's a little bit tricky, but we're going to start with the change of base formula. So one more time, I'm going to write the change of base formula. So change of base formula one more time is this. Right? We just did this 3 times now. So how do we handle logarithm multiplication? Well, first off, what I want to do is I want to clear fractions, right? I'm examining this formula that I have, and I want to clear the fraction. So to clear a fraction, that means you multiply by the denominator, right? If I multiply it by log base b of a on the right-hand side, well, then, and just to write it here, if I multiply by log base b on a, what's going to happen? Well, this piece and that piece are going to cancel out, right? But whatever I multiply on the right-hand side, I also have to multiply on the left-hand side, right? So I also have to multiply over here, log base b of the value a. But let's go ahead and clean this up a bit. Cleaning this up, what this looks like now is I have the log, and I'm just going to write this piece first. You'll see why in a second. So what I have now is log of base a on the value x and log of base b on the value a is equal to log of base b on the value x. So this is still change of base formula, but notice how we no longer have division going on. And what I also want you to take away is notice the similarity. We have a base of value a in one logarithm, and in the other logarithm, the value is that same base, right? The a is the base here, and it's that same number is the value in this one. So what does this say? This says that if we have the logarithm to some base, it doesn't matter what it is, and it has some value, if we multiply by a logarithm of a different base, as long as this value matches the base of the first logarithm, well, what you can do is you can condense it into one log where the other pieces of information just fall out. Notice that your base b, the base that doesn't match a value, just directly corresponds to the base of your new log, and the value that doesn't correspond to a base is still the value of your new log, okay? I know there's a lot of lines and there's a lot of circles going on, so let me try to clean this up one more time. So to color code things, because I feel like that often helps, again, notice that the base of one log matches the value in the other. And then, as long as you have that, you can do this logarithm multiplication such that you get a new log, only one, where your base is going to be the base that didn't match any value, and your value is going to be the value that didn't match any base. Okay, let's go ahead and do 2 examples together, and then I'll set you off on your classwork. Okay, so first example here. What I want to do is I just want to simplify the following. Okay, so simplify log base 3 with the value 10 on multiplied by log with the value 5. Okay, so before you proceed, the first thing that you should figure out here is what's my base for this logarithm. Again, if it is omitted, then it is understood that the base is 10, right? If it's omitted, then you know it's the common log, which tells you base is 10. Okay, what you're looking for here to do logarithm multiplication is you're looking for a base to match a value, and it shouldn't be in the same logarithm. We have this rule where if within the same logarithm, if the base matches the value inside one single logarithm, we know this simplifies down to just be 1. That's not what we're looking for here. What we're looking for is the base of one logarithm to match the value in the other logarithm that it's being multiplied by. So we look and we say, okay, well, Does 3 match 5? And the answer is no, right? So, okay, that's not going to pan out. But we have a value 10 in one log, and we have the base of 10 in another. Those are the matching pieces. So yes, we can take these two logarithms and we can condense them. We can take the logarithms, do the multiplication, and the multiplication will always yield one log, where the base of this new log is going to be the leftover base. So the leftover base is 3, and the value of this new log is the leftover value. So 5. Okay, and that's it. That's simplifying. That's all we did. We had two logarithms being multiplied against each other. We were just looking for the matching pieces, and as long as we have a matching pair of a base and a value, then we can just condense it into one log where the pieces are the leftover pieces. And that's it. You're just taking the leftovers and moving it over, right? Everybody loves leftovers. Cold pizza is the best. Okay, so let's move on to a second example here, and maybe this one will be a little bit more challenging, but it should hopefully still get the point across. Okay, so I'm just going to erase this example, but I'm going to keep this right up top right here. Okay, second example is, again, I just want to simplify the following. Okay, so if I have two logarithms being multiplied, I want to find a way to simplify them. So let's say we have 2 times log base 2 on the value 3 multiplied by log base 9 on the value 5. Okay, so at first glance, this doesn't look like this is going to work out. Why doesn't it look like it's going to work out? Well, again, you're supposed to be matching one base from one logarithm to the value of the other, right? And we see here that if we're talking about our two pairs, these don't match up, right? 3 doesn't match to 9, 2 doesn't match to 5. So are we stuck here? Well, the answer is no, right? The reason that it's a no is because we have this coefficient here. And what does the power rule allow us to freely do? It allows us to freely take our coefficients and move it to the exponent of the value of our logarithm, right? And vice versa. If we add an exponent, we can make it a coefficient. If we have a coefficient, we can make it the exponent. So what I'm going to do is I'm going to simplify this logarithm first. Okay, so I'm going to say, okay, well, this is equivalent to, and I'm just writing an equal sign underneath for the sake of space here. So this is equivalent to log base 2 of 3 squared. I took my coefficient and I moved it to the exponent's place, right? The exponent is now tied to the value inside that logarithm. That value is 3. So I have log base 2 on 3 squared times log base 9 on the value 5. And what this allows me to do when I simplify this one more time is I have log base 2 of 9, 3 squared is 9, and log base 9 of 5. And now we have a matching pair, right? We have a value of 9 in one log and a base of 9 in the other log. And when this matches up, we can then go ahead and do that condensing, right? So what happens when we condense? We're just going to be left with one single logarithm, right? When you multiply two logs together, as long as you have that matching pair, you're just going to have one logarithm where it's the leftover pieces, right? What is the base that doesn't have a matching pair? Well, it's 2, right? So we're just going to have log base 2. And what is the value that doesn't have a matching pair? Well, that is 5, right? So that means our final condensed logarithm is log base 2 on 5. So notice how we started with 2 logarithms, and we can condense it down to 1. Okay, and also the same is true for expanding. If we started with this logarithm, well, we can always make it log of base 2 with some value. It doesn't matter what that value is, right? So I can, I'm just going to write this over here in green. We can always make it log of base 2 on some value. I'm just going to call it a, and multiplied by log of. And what should it be? Well, again, the idea here is we need a matching piece, right? So log of a on the value 5. Again, notice that these are the matching pieces. So that means that the 2 and the 5 are the leftovers, just like over here, right? 2 and 5 are leftover. In this case, our a from actually doing this example was 9, but it doesn't have to be 9. The point that I'm illustrating here is that if we wanted to expand one logarithm into 2 logs being multiplied against each other, well, all you have to do is just keep a log with the same base that you were given and keep a log with the same value that you were given, and the other values here just have to correspond to each other, right? A and A just have to match up. Doesn't matter what that number is, as long as that number is not 1 and it's greater than 0. Okay, so for the sake of it, just for the sake of argument, we would get the exact same answer as if we had log base 2 of 726 times log with base 726 on the value 5. These are entirely equivalent. Even if it doesn't look like it, this and this will both simplify you down to give log base 2 of 5. Okay, again, the entire idea here is just finding that matching base and value. If you have the matching base and value, you're good to go. And then you can simplify it down, and whatever's left over are the pieces that you're bringing into your new logarithm. Okay, so with all that being said, I want you guys to go ahead and try your second classwork assignment. Okay, so the second classwork assignment is as follows. Again, it's one more time of this logarithm multiplication where you're simplifying the following. So you have log with base 7 on the value e, and this is being multiplied by ln 7. Okay, so go ahead, give this a shot, see what you can come up with, and we'll take it in just a second. Okay, so the idea here, once again, is you're looking for matching components, right? And yeah, at first glance, you do have a matching component, right? 7 and 7, but we can't immediately break it up because we don't know what the base is of the natural log, or do we? It's a natural log, right? So the first thing that you should do is you should just convert that natural log to be in the same form as the other logarithm. So I'm just going to write this as log base 7 on the value e, and this is also log on with the base of e on the value 7. But then you say to yourself, wait a second, hold on. We have 2 matching pairs. We have the base of e matching to the value of e, and we have the base of 7 matching to the value of 7. What's going on here? Well, if we proceed, and what I'm hoping that about half the class did it one way and half the class did it the other, you're going to arrive at the same answer either way. So let's do it the first way, and the first way that I'm going to do it is I'm going to do it using the matching pairs of the 7s, right? So if I have a matching pair of 7s, the base is a 7, the value is a 7, what that tells me is I have leftover log with my leftover pieces, right? What's left over? Well, what's left over is the other pair, right? The e and the e. So that means I have log of base e on e, and well, we know that that's the natural log of e, and we have a property for this, right? Natural log of e just simplifies down to be 1. And of course, if you didn't see that, maybe you even saw it here. Again, remember our property. If we have log of any number and the value and the base match within the same logarithm, it should always simplify down to just be 1, right? So if you did it with that pair, that's totally fine, and you got it to be 1. And now what I'm going to do is I'm going to do it using the other pair, right? So the other pair is where I have, if I'm considering the e and the e as the pair that, are matching, then what's left over? Well, what's left over is log base 7 with the value 7, right? The 7s are now what's left over. And, well, again, we just talked about this property. If we have the logarithm of any number and the value and the base both correspond to each other, then it's just 1. So you get 1 either way. However you simplify this, you should get 1. Okay? And that's it for the second classwork. So what I'm hoping that you guys understand here is that for division, for addition, and for subtraction, the bases have to match. Multiplication is the only one that's kind of tricky. Multiplication, there does have to be a matching, but it's not base to base. Multiplication, it has to be base to value. And that's where multiplication is a little bit tricky for logarithms. Otherwise, you're okay to, for logarithm addition, we have that product rule. For logarithm subtraction, we have the quotient rule, we have the power rule. We just talked about change of base, which allows us to divide logarithms because we can, change the base freely. And as a consequence of the change of base formula, we see that we can actually multiply logarithms as long as we have corresponding pairs between the base and the values of, one log to another. Okay, so with all that being said, that's it for change of base. There's one last topic that we have to go through, and that will be absolutely it for logarithms. Okay, so the last thing that we have to do is trying to find a logarithmic equation in the following form. So y is equal to a plus b log of x. Okay, so what we're trying to do is we're trying to find it in this form. Okay, so if you had a question that said find, a logarithmic equation in this form, these are the set of steps that you have to follow to be able to get this. Okay, so there's essentially a 5-step process here. One of the steps is not going to be intuitive. In fact, unless you have taken some form of linear algebra before, this is something that you've never seen before. It's something that I wanted to get to in this semester, but it's super deep in the textbook, and we have to cover other stuff first that's more prevalent. So we might not get to it, but if we don't get to that material, pre-calc absolutely will get to it. And again, there's a linear algebra course that's basically this entire subject. Okay, so fair warning, you've never seen this before, and it's not. Again, it's totally okay if you're confused. We're going to go through it pretty slowly, okay? So there's a 5-step process to this. Your first step, and for the record, whenever you're trying to find something in this form, you're always going to be given 2 pieces of information, okay? So essentially, if you guys remember when we were solving for exponential equations in this form, if you remember, c times a to the x, you were given 2 pieces of information. Why were you given 2 pieces of information? Because you had 2 variables that you were solving for, right? You were solving for c and you were solving for a. The same is going to be true here. In this case, we're solving for a and we're solving for b. The logarithm on x, you're not solving for. Y, you're also not solving for. Those are going to be where you're plugging in your solutions, okay? So here's your 5-step process for solving something in this form. Your first step, you're going to create 2 different equations using the solutions that you're given, okay? So create 2 equations given your solutions, okay? Second step, and this is the part where, I'm going to write it and it's going to make no sense because this is where, again, you've probably never seen this before, okay? You're going to subtract one equation from the other, okay? So subtract one equation from the other. We'll go through that slowly in, the following example. The third step is you're going to simplify and solve for b, okay? So solve for b. You're going to plug b back into either of the equations that you just, that you solved for, or that you set up, right? Because again, from step 1, you set up 2 different equations, right? So what you're going to do is you're going to plug b back into either of your equation. Plug b into either equation and solve for the other variable, which is a. And your last step, which is kind of trivial, but just for the sake of it, you're going to plug a and b back into either equation and then simplify if needed. Okay, so then plug both back in and simplify. Okay, so I know that sounds like a lot of talking. And again, we're going to go through an example of this together. There's one homework question that is going to, correspond to this example. Okay. So what I really recommend is if you struggle with the homework question, come back and watch this one, because this one will give you a good idea on how to solve the homework. Again, the steps are going to be the same. There's one tricky thing in the homework question that I'm not going to go over right now, but we might go over it, in class. Okay. But the steps are going to effectively be the same. Okay, so hopefully you got this down, and I'm just going to zoom out real quick to give you a chance to pause and write this down if you need to. Again, this is just if you are trying to get it in the form y is equal to a plus b times log of x. Okay, so let's do our example together. Okay, example. Let's say given the following, so given 3, 3, and 9, 1 are solutions, find the equation in the form that I just wrote before. A plus b times log of x. Okay, so our first step is pretty simple. We're going to create two equations using the solutions given. Now, I remember there was a little bit of confusion even on the quiz as far as where you're plugging 3, 3 and 9, 1 into. Again, 3 is your input, right? And what is your input in an equation? Well, it's generally going to be your x. And that means that this is your output, which corresponds to y. And same thing with the 9 and the 1, right? So the two equations that you're setting up, you're just plugging in these points for x and y. You don't know what a and b are yet, but that's okay. All right. So setting this up, what we're going to have is we're going to have for 3, 3, we're going to have 3 is equal to a plus b log of 3. Okay. And for the second one, we're going to have 1 is equal to a plus b log of 9. Okay, easy enough, right? Again, we had our y. Y for the 2 points was 3 and 1, so we have 3 and 1 for our y's. And then for our x's, that was 3 and 9. So that's where we're writing that, right? Okay, the second step, and this is the one where I imagine there's going to be a decent amount of confusion here. The second step is you are subtracting one equation from the other, okay? So what does that mean? Well, notice how I wrote these in columns, right? I have my y's over each other. I have my a's over each other, the b log, whatever, over each other, right? These are all in columns. So what I'm going to do is I'm going to subtract the bottom equation from the top. So what am I doing here? Effectively, what I'm doing is I'm subtracting 1 from 3. So this gives me 2. What's positive a minus a positive a? Well, a minus a just drops out, right? And a minus a is just, well, 0. So a goes away, which is really important for us because now we'll only have one variable to solve for. We'll only have the b to worry about, right? So, okay, well, now we have b log 3 minus b log 9, which we can't really simplify just yet. So we're just going to write this as b log 3 minus b times log of 9. Okay, again, the idea is you are just subtracting each column. You're subtracting your y from your y, so your 3 minus 1. You're subtracting the a minus a, and then you're subtracting the last piece, which is, the b log 3 minus b log 9. You can't cancel anything out there, so you just leave it for what it is, b log 3 minus b log 9. Okay? Okay. So that's the thing that I'm sure you've never seen before. This comes up in linear algebra, where as long as you have the same variables in two equations, you can add or subtract them from each other. Okay, that's just a thing that we can do. But, either more on that later or more on that in some future math class. This is probably the only time in this class that you're going to see it, more than likely due to time constraints. So in any event, 2 is equal to b log 3 minus b log 9. Well, we have a factor of b in 2 spots, right? So what I'm going to do is I'm trying to solve for b. So I'm going to factor b out so that I only have one instance of it. So that means I have 2 is equal to b times log of 3 minus log of 9, right? All I did is I pulled b out. I just factored that out. Okay, but we have a rule here. What is our rule for logarithm subtraction as long as the logarithms have the same base? And they do because they're both common logs. Well, logarithm subtraction says, well, I can condense it into one log with the same base, and then the two values are just being divided, right? So this is the same thing as 2 is equal to b times log of 3 over 9. And in the same step, I'm just going to go ahead and simplify. 3 over 9 is the same thing as 1/3, right? Okay, so one last little piece that I want to do here, and I want to try to simplify this as much as I can. So simplifying this as much as I can, 1/3, if we remember our exponent rules, 1/3 is the same thing as 3 to the negative first power. There's a really good reason that I'm doing this. So I'm going to convert 1/3 to be 3 to the negative 1. Okay? And now when I do that, the reason that I did this is because what can we do with the power rule of logarithms? The power rule says I can take my exponent and bring it out front, right, to be a coefficient. So this simplifies to be negative b times log of 3. And now all I want to do is I just want to solve for b. So solving for b, I'm just going to divide both sides by negative log of 3. So dividing both sides by negative log of 3 gives me b is equal to negative 2 over log of 3. Don't worry about what log of 3 is. Honestly, it is what it is. That's not, terrible big deal. We have some value. B is equal to something, right? This is as simplified as we can get it, but we have an answer. Again, remember in the last time when we were solving for f of x is equal to c times a to the x, you didn't always get a number for c. Sometimes, c looked weird. Sometimes we got c is equal to 1 over a, right? Or we got some other weird thing. It's okay for you to get some value as long as you're just maintaining consistency that this is what you're going to be plugging in for b in, later on. Okay, so that was our second step and our third step, right? Second step said subtract the equations, one from the other. And the third step said simplify and solve for b. So we solved for b. So what's our fourth step? Fourth step says plug b back into either of the equations that we had from the first step and then solve for a. So that's fine. One of the equations, the one that I'm going to plug it into is the 3, the 0.33. So that's where we had 3 is equal to a plus b log of 3. And again, now we know what b is, right? So plugging b back in, we have 3 is equal to a minus, remember b is negative, so a minus 2 over log 3 times log 3. And hey, something miraculous happens. We have log 3 over log 3, right? These cancel out, just, by pure and utter happenstance. So we're just left with 3 is equal to a minus 2. And now that we have 3 is equal to a minus 2, we can solve for a. And solving for a, we get a is equal to 5, right? Okay, last step. What's the last step? The last step is we have to get this in the following form. We have to get it in the form y is equal to a plus b log of x, right? That's the form that we have to get it in. So plugging our values back in, we have y is equal to, we solved for a is 5, so we have 5. B is negative, so once again, that plus is going to be a minus, and b was 2 over log of 3, and this is still being multiplied by log of x. Okay, what I'm going to do here is I'm going to move the log of x over the fraction, right? We know this is true, right? If we have, when we're talking about fractions and multiplication, if we have 2 times 3 over 6, this is the same thing as 2 times 3 over 6. And also it's the same thing as 3 times 2 over 6, right? What I'm getting at here is that if you have two things being multiplied up top, you can always move them out, right? You can always move one of them out and just have the division of the other two, right? And the reason for this is because multiplication and division are of the same order when you're talking about order of operations, when you're talking about PEMDAS. So this is all equivalent. So what I'm going to do is I'm going to move my 2 on the outside of the fraction, and I'm going to move the log of x to the top of, the numerator here, right? It's being multiplied against the fraction, so I'm going to put it up top. So what I now have is y is equal to 5 minus 2 times log of x over log of 3. And there's a very good reason that I did this. The reason that I did this is, now notice we have a division of logarithms where the bases are the same. Well, this is change of base formula, right? What was change of base formula? Change of base formula is, if we have log of a to the x, this is log of some other base of x over log of that same base of a, right? So notice, what's my b in this case? What is my base of both of these? Well, it's 10, right? So this is effectively log, and I'll actually write the 10 this time, even though we don't need to. Log base 10, and what's my value of the top one? Well, my value is just x. We don't know what it is. It's, it's our input. So we have log base 10 of x all over log base 10 of 3. And according to our change of base formula, what should happen? Well, when we condense this into one single logarithm, we should get, again, we should just get one single logarithm where the new bases kind of went away, right? Those didn't matter. If we consider b and b here, there is no b in our other logarithm. So those bases don't matter. What is my base here? Remember what was happening. The bottom value becomes the base, right? So we have log of base 3, and the top value is the value that goes to our value of the new log. So that's going to be log base 3 of x. So finally, our final answer is we have y is equal to 5 minus 2 log base 3 of x. And we have achieved our goal of getting a logarithmic equation in that following form. Okay, I know that this is really tricky. There's a lot of intricate details that go into this, and in step 2, it's doing something that, again, I'm sure plenty of you guys have never seen before. That's why I totally understand if this one is confusing. I really recommend watching through this one more time to really hammer in the details of what you're supposed to do. Again, it's just a series of 5 steps, right? You can follow 5 steps. If you just do the steps in order, I'm sure you can do it. The idea, again, just to run through the steps one more time, you're going to set up 2 equations given your 2 solutions, right? What were our 2 solutions? Our 2 solutions were 3, 3, and 9, 1. So we set up 2 equations somewhere. There we go. We set up 2 equations as such, right? We just plugged in for y and for x. Second step, and this is probably one of the more confusing steps, is subtracting one equation from the other. All you're doing is you're subtracting the columns, right? You subtract the y from the y, you subtract the a from the a, and you subtract the b log 3 from the b log 9, right? The b log from the b log. Okay? So you realize whenever you do this, a minus a is always going to cancel out. And again, that's by design. We do this for a reason. We do it because we want to only work with one variable at a time. So notice how we're only solving for b now. And now all you're doing is you're simplifying down this equation here, and you're solving for b. You simplify down just by factoring the b out, and by using just the regular the regular logarithm rules that we all know by now, hopefully. Product rule, quotient rule, power rule, right? These are all things that we've gone through time and time again, right? So we end up with an answer for b, and what we do is we plug it back into either one of the equations. Now, granted, I plugged it into this equation for a reason, and the reason I plugged it in is because, again, we defined b to be a divisor of log of 3, right? When we solved for b, we found that we had a division of log of 3, and it just happened that in the top equation, I had a multiplication of log of 3. These are things that when you do math for long enough, you start to pick up little tricks, little things that make your life easier. But even if you didn't see that, you can absolutely plug it into this equation. It'll take a little bit more work, but you can get there. You can absolutely still simplify that down, and it'll still give you the same answer for A. Okay, but I did this because it saves on work. So we noticed that we had the multiplication of log of 3 times the division of log of 3, so those would cancel out, and that left A to be pretty trivial to figure out. So we solved for A. And now once we solved for both a and b, we tried plugging it into the form, and the last thing that we had to do was we had a division of log of 3, but a multiplication of log of x. So we used the change of base formula to make this division of logarithms one single logarithm. Okay, so I know that this one's pretty confusing. Just try your best with it and try your best with the homework. And if it's really a problem, then of course come talk to me and we'll sort through it together. Okay, but that's it for this lecture, guys. I've been talking for just about an hour now, so good time to stop for sure. Try your hand at the homework, and I will talk to you next time. Enjoy the rest of your night or day. Have a good one.